So guys, I'm going to discuss sleep and wake up. Both Peterson's solution and the solutions using TSL, test and set lock, or XEHG exchange are correct. But both have the defect of requiring busy waiting. In essence, what these solutions do is this. When a process wants to enter its critical region, it checks to see if the entry is allowed. If it is not, the process just sits in a tight loop, waiting it is. Not only does this approach waste CPU time, but it can also have unexpected effects. Consider a computer. Say you have a computer here, and you have two processes, H with high priority, with low priority. The scheduling rules are such that is run whenever it is in ready state at a certain moment, with L in its critical region, run. Now H begins busy waiting. L is never scheduled while H is running. L never gets the chance to leave its critical region, so H loops forever. This situation is sometimes referred to as the priority one problem. Now, let us look at some interprocess communication primitives that block instead of wasting CPU time when they are not allowed to enter their critical regions. One of the simplest is the pair sleep and sleep is a system call that causes the caller to block, that is, be suspended until another process wakes it up. The wake up call has one parameter, the process to be awakened. Each have one parameter, a memory address used to match up, sleeps, and wake ups. This is the outline for the presentation, but I'm only going to discuss until because the reporters already discussed this one. Okay, so we'll start with the producer-consumer problem. As an example of how these primitives can be used, let us consider the producer-consumer problem. It is also known as the bounded buffer problem. Two processes share a common fixed-size buffer. One of them, the producer, puts information into the buffer. Here, producer puts information into the buffer. Okay? And then, of course, we have the other one, which is consumer, which takes the information. It is also possible to generalize the problem to have M procedure producers and N consumers, but we will consider only the case of one producer and one consumer, because this assumption simplifies the solutions. Trouble arises when the producer wants to put a new item in the buffer, but it is already full. The solution is for the producer to go to sleep, to be awakened when the consumer has removed one or more items. Similarly, if the consumer wants to remove an item from the buffer and sees that the buffer is empty, it goes to sleep until the producer puts something in the buffer and wakes it up. This approach sounds simple enough, but it leads to the same kinds of race conditions we saw earlier with the spooler directory. To keep track of the number of items in the buffer, we will need a variable which is count. Maximum number of items the buffer can hold is n, the producer's code will first test to see if count is n. If it is, the producer will go to sleep. If it is not, the producer will add an item and increment count. The consumer's code is similar. First, test count to see if it is 0. So, if it is, go to sleep. If it is not 0, remove an item, increment counter. Each of the processes also tests to see if the other should be awakened, and if so, wakes it up. The code for both producer and consumer are already posted in these slides. Okay. So, to express system calls such as sleep and wake up in C, we will show them as calls to library routines. They are not part of the standard C library, but presumably would be made available on any system that actually had these system calls. The procedures insert item in the producer's code and remove item here in the consumer's code, which are shown, handle the bookkeeping of putting items into the buffer and taking items out of the buffer. Now let us go back to the race condition. It can occur because access to count is unconstrained. As a consequence, the following situation could possibly occur. The buffer is empty and the consumer has just read count to see if it is 0. At that instant, the scheduler decides to stop running the consumer temporarily and start running the producer. The producer inserts an item in the buffer, increments count, and notices that it is now 1. Reasoning that count was just 0 and thus the consumer must be sleeping, the producer calls wake up to wake the consumer up. Unfortunately, the consumer is not yet logically asleep, so the wake up signal is lost. When the consumer next runs, it will test the value of count if previously read, finds it to be 0, and goes to sleep. Sooner or later, the producer will fill up the buffer and also goes to sleep. Now, both will sleep forever. The essence of the problem here is that a wake up sent to a process that is not yet sleeping is lost. If it were not lost, everything would work. A quick fix is to modify the rules to add a wake up waiting. Okay. So when a wake up is sent to a process that is still awake, this bit will be set. Later, when the process tries to go to sleep, if the wake up waiting bit is on, it will be turned off. But the process will stay awake. The wake up waiting bit is a piggy bank for storing wake up signals. The consumer clears the wake up waiting bit in every iteration of the loop. While the wake up waiting bit saves the day in this simple example, it is easy to construct examples with 3 or more processes in which one wake up waiting bit is insufficient. We could make another patch and add a second wake up waiting bit, or maybe 8 or 32 of them, but in principle, the problem is still there. We will now go to semaphores. Semaphores solve the lost wake up problem, as shown in this figure. To make them work correctly, it is essential that they be implemented in an indivisible way. The normal way is to implement up and down as system calls, with the operating system briefly disabling all interrupts while it is testing the semaphore, updating it, and putting the process to sleep if necessary. As all of these actions can take only a few instructions, no harm is done in disabling interrupts. If multiple CPUs are being used, each semaphore should be protected by a lock variable with the TSL or XEHG instructions used to make sure that only one CPU at a time examines the semaphore. Be sure you understand that using TSL or XEHG to prevent several CPUs from accessing the semaphore at the same time is quite different from the producer or consumer busy waiting for the other to empty or fill the buffer. The semaphore operation will take only a few microseconds, whereas the producer or consumer might take arbitrarily long. This solution uses 3 semaphores, one called full for counting the number of slots that are full, one called empty for counting the number of slots that are empty, and one called mutex to make sure the producer and consumer do not access the buffer at the same time. You know that mutex stands for mutual exclusion. So full is initially 0, empty is initially equal to the number of slots in the box. Mutex is initially 1. Semaphores, mutex is initially 1. Semaphores that are initialized to 1 and used by 2 or more processes to ensure that only one of them can enter its critical region at the same time are called binary semaphores. If each process does a down just before entering its critical region and an up just after leaving it, mutual exclusion is guaranteed. Now that we have a good interprocess communication primitive at our disposal, let us go back and look at the interrupt sequence of figure 2-5 again. In a system using semaphores, the natural way to hide interrupts is to have a semaphore initially set to 0 associated with an IO device. Just after starting an IO device, the managing process does a down on the associated semaphore, thus blocking immediately. When the interrupt comes in, the interrupt handler then does an up on the associated semaphore, which makes the relevant process ready to run again. In this model, step 5 in the figure for test and setback consists of doing an up on the device's semaphore so that in step 6, the scheduler will be able to run the device manager. Figure 2-5 is the interrupt sequence, which I will post in slide 7 of this presentation. So, of course, if several processes are now ready, the scheduler may choose to run an even more important process next. So, in the code, you can see here, we have actually used semaphores in two different ways. This difference is important enough to make explicit. The mutex semaphore is used for mutual exclusion. It is designed to guarantee that only one process at a time will be reading or writing the buffer and the associated variables. This mutual exclusion is required to prevent chaos. We will study mutual exclusion and how to achieve it in the next topic. The other use of semaphores is for synchronization. The full and empty semaphores are needed to guarantee that certain event sequences do or do not occur. In this case, they ensure that the producer stops running when the buffer is full and that the consumer stops running when it is empty. This is the interrupt sequence mentioned in slide number 5. Okay, step 5, C interrupt service runs, typically reads and buffers input. Step 6, scheduler decides which processes to run next. Okay, so that's what was mentioned in the example in slide number 5.